quite a bit of graphing today. We're talking about properties of exponential functions, and we already used those when we were talking about our savings accounts and increasing. And then we had some that had the exponential decay going on. So what we want to do is explore the properties of functions in the form y equals a times b to the x. And definitely we are going to get to graphing exponential functions that have a base of e. Wait a minute. A base of e. Isn't the base supposed to be a number? Then we're going to put a number in for b. E is a number. We have it on our calculator. We just never used it before. So we're going to learn a new number as we go through this section. Might not get there today, but definitely will tomorrow. And if we get to the point where we need calculators, I'll get you one. This one says f and g are exponential functions. And I look over there and I think, well, they're both growth. They're going up from left to right. Okay, so is the graph a compression, a reflection, or a translation? Well, let's investigate. Let's see. This point looks like it goes right over there. That seems like they're moving at 2, so let's check one up here somewhere. This looks also like they're moving at 2. So this could be a translation. Absolutely could be. Could be a translation. And we are not going to get into this in as much detail as you see this stuff here, because what we'll do is you guys are good at the graphing. I'm not going to spend a lot of time on something that's just going to confuse you before we start doing graphing. But you know what I also think about this graph? If I were to put my hand at the bottom of the graph and my hand at the top of the graph and I squished it down, it would also do that. It would squish it. So with exponential growth and decay, what appears to be a translation could also be a compression. So what that does is it really gives us 2 ways to do the same thing for the graph. So that's pretty unique when we're talking about all the graphs that we've done so far. That doesn't happen for square roots, doesn't happen for cubed roots, doesn't happen for our V-shaped graphs. But for exponential growth and decay, because they are unique in the way that they look, a compression could be a translation. It's just whatever you see and it's easiest for you is what you would use. So what we have to do is we have to get back into A, H, and K. And what we always want to remember is A is going to be part of our shape. H and K we always wait for. A is a part of our shape of the graph. And once we have that, then we just count. Then it's H is going to tell us to go this way, K is going to tell us to go this way. So what we have to do is see families of exponential functions. When we want to graph square roots, we talked about families of square root functions. We got our nice little table that we always used all the time, and we went with it. Now, this is telling us stuff we already know. If the value of A that's in front is bigger than 1, it's going to be a stretch. Absolutely will be. If the value of A is between 0 and 1, a fraction between 0 and 1, fraction between 0 and 1, then it's going to be a compression. If it's negative, I'm going to flip it over the x-axis. Definitely going to do that. And then our translations, wow, look where H gets to go this time. Look at that little bugger right there. It's part of the power up here. That's going to be unique. But what's not unique is we still have to think opposite. If anything's working with X, we always have to think opposite. And then K, still hanging out in back, so that's pretty normal. But pretty weird here how our X, because it was the power, has to have H attached to it as the power itself. And then, all together, A, H, and K. Looks kind of scary, but you know what? You're going to be really good at this. Once we get a standard table down, we'll be just fine. We'll be able to do whatever we need to do with these. However, we might need one table for growth and a different table for decay. Because what we're going to want to really see on the growth is what's going on over here. I mean, that's what we want to see. But when we're talking about decay, we're going to want to know more about what's going on the left side. So we might pick more positive numbers to put into our chart for growth and a few more negative numbers to put in when we're talking about decay, just so that we can see the side of the graph that really makes a difference. Now, why do I say that? We know where this is going in an asymptote. It's never going to cross it, so that's where we're going to aim. Over here, this is going to approach an asymptote. We find it. We don't need to worry about how to draw that part. We already know. Because an asymptote is a line that you approach but you never cross. So we need to know the parts that are making a difference on these graphs. And that, of course, comes from the shape. That's what we're going to use. So let's see. They jumped us right into this. It says, how does the graph of y equals negative 1/3 times 3 to the x compare to the graph of the parent function? So the first thing I do is think, okay, well, the parent function would be before there's any a on it. So right here, I'm looking at this negative and I realize, well, it's going to reflect over the x-axis. And then I look at the 1/3 and I realize it's going to be a vertical compression. So that's how it's going to compare. But we want to see it. You know, what does it look like when you put a negative 1/3 in front of this thing? With a 3 as the base, is this a decay or growth graph? It's a growth graph. So notice the book put in -2, -1, 0, 1, and 2. Well, you could kind of use that standard every time. But for growth, I might even add a 3. I might want some more of those positive values to see exactly what's going on. So if it were just y equals 3 to the x, we know it's not, but if it were, what we would do is raise 3 to this power. And like I talked about yesterday, you could always use a calculator for that if you're just sitting there going, oh my gosh, you can't remember that negative power stuff. But in your head, you'd take 3 and flip it to get rid of the negative, so it would be 1/3, and then you'd square it. And that would be 1/9. But those of you that that's not happening for, don't worry about it, because you can do this. 3 to the -2. And you can even write the decimal down. It wouldn't bother me at all. But if you wanted to be fancy, you could go to math number 1 and switch it back into a fraction. 3 to the -1 is just the reciprocal. You flip it. To the 0 power is 1. 3 to the first is 3. 3 squared is 9. And 3 to the third is 27. So you're home, why'd you put that on there? We're not graphing 27. Our window's from -10 to 10. We're not done. Remember, what we want to see is A with the base. That's going to be our shape graph. So what I have to do now is take -1/3 times all of this. Because the order of operations says you're going to do 3 to the x first, and then you're going to multiply everything by -1/3. Okay. 1/9 times -1/3. Well, with fractions, you do top times top and bottom times bottom. So that'll be -1 over 27. So -2, -1 over 27 will be the first point I get. Hey, -1 over 27, that's going to be really close to 0. It should be. This is growth. It should be looking like this. Absolutely should. I have 1/3. I'm going to multiply that by a -1/3. That's going to give me a -1/9. 1 times -1/3 is, of course, -1/3. So it's starting to get a little higher. Not a lot. 1/27, 1/9, -1/3. Now we've got a 3, and 3 times -1/3 would be 3 over 1 times -1/3. So that's going to be -1. Numbers starting to get a little bit bigger. -1/3 of 9. Remember, it's going to be like 9 over 1. So you'll get -9 over -3, which is -3. And then this is the reason I put 27 on there. So far, we have a graph that's kind of doing that, nice and slow. But if we put the 3 on here, -1/3 of 27, that's going to give us negative 9. And that really shows us exactly where this graph is going to go. Let's get them on there. Negative 2, negative 1/27th, just a teeny little bit below the x-axis. Negative 1/9, still just a teeny bit below the x-axis. 0, negative 1/3. Okay, there's that 0a again. 0a was negative 1/3. 1, negative 1. 3, negative, whoops, wait a minute, not 1, negative 1. 1, negative 1/3. That's right, this one was really going slow. 3, negative 1. And then, why do I keep wanting to say 3, negative 1? Oh, I'm looking at these two. Come on, eyes, use the first and last. 2, negative 3. And then 3, negative 9. Now we start to see, yeah, this is going to drop pretty fast. Just took it a while to get going. So it's going to look like that. Now we check. Did it do what we said it was going to do? Is it reflected over the x-axis? It should have been up here. I mean, if everything was positive, it would have been up above. It is flipped below the x-axis. The compression is going to be really hard for us to see, and that's because the parent function we were using before had a 2 here. So we kind of have to trust that our math, multiplying that by that negative 1/3, gave us that compression as we go through there. There it is. So now what they want us to do is take a look at the domain, range, asymptote, and y-intercept of what it was beforehand and what it is now. So I'm going to switch colors. You guys should grab either a colored pencil out of the bag, or if you have a different colored pen or something else. And I'm going to go back and graph it without the negative 1/3. So we can see, what happens with the domain and range if you throw that negative 1/3 in front. So this time around, I'm graphing in the green, negative 2, positive 1/9. Negative 1, positive 1/3. Let's see. 0, 1. 1, 3. And 2, 9. Write that equation y equals 3 for x up there. So before you did any of that negative 1/3, the graph would look like that. Again, it's hard to tell the compression. If you look at this and you think squish it and flip it, yeah, it's a little wider. But we can see that. So now what we're going to do is we're going to make a table out of this wonderful stuff down here. And we're going to take a look at our domain, our range, asymptote, and y-intercept of the green one. And then of the red one. Okay, to use the dot. I'm just going to do parentheses there. I'm going to have a decimal. All right. Domain is about the x's. So I asked myself, are there any numbers that you can't raise 3 to that power? Any real numbers in there? You can raise 3 to any power you want. The domain is going to be all reals. But my green graph did not use all the y's. My green graph didn't use anything down here. It's using things that are bigger than 0. So y is going to be greater than or equal to 0. Oops, can't use the equal to. Now why can't I use the equal to? You remember from yesterday? Yes, it's an asymptote. So we kind of connect these two things and say, well, it has to be greater than because y equals 0 is my asymptote. And then the y-intercept was just what did we get when we put a 0 in? Well, it was 0, 1. Because remember, it's 3 to the x, there's an imaginary 1 out front. That's all it is. Now my red one. Things sure changed. Okay. Well, we still use the same table, so we could still put in any number we want. But that negative flipped it down below the x-axis. So now y is less than 0. Did the asymptote change? Still not touching that x-axis, so it's still y equals 0. Y-intercept definitely changed, because now our a value was negative 1/3. So it went through 0, negative 1/3. So what we're doing here is we're going a little bit further with our investigation than saying, okay, there's a negative, it's going to be reflected over the x-axis. It's a 1/3, it's going to be a vertical compression. And we're seeing stuff can change, and some things don't. The domain is the same, but because of the negative, instead of y is greater than 0, now it's y is less than 0. And our asymptote didn't change, but because of a, our y-intercept did change. And again, that's going to be our parent function, and then we're going to move things from there. So let's go down to this one. How does the graph of y equals negative 0.5 compare to the graph of the parent function? Okay. What's the negative doing again? Left over the x-axis. .5. We did that on purpose. That's 5/10. 5/10 is 1/2. What's that going to do? Compression. Vertical compression. Vertical compression. Factor 1/2. So I start thinking, isn't that just what we did in the last one? Didn't we have a reflection over the x-axis and a compression? So this ought to do pretty much the same stuff. So how we're going to graph it is we're going to go back to a standard table and say, okay, well, the book was just using -2, -1, 0, 1, and 2. Might as well give those a try. And our original parent function is now 5 to the x. So that's what's going to go in here. Okay. So 5 to the -2. Got to flip it and make it 1/5, and then square it. That's 1/25. 5 to the -1, you just flip it, 1/5. 5 to the 0 is 1. 5 to the first is 5, and 5 squared is 25. That thing's going up fast. But sure, there's a 5 for the base. So let's go ahead and get this one on there, just like they had us do in the last one. -2, 1/25, -1, 1/5, 0, 1, 1/5. And then we're just going to have to aim almost straight up, because this one is going to 225. I'm going to change color. Because really, what we want to see is the parent function with a. So that means we're going to take -0.5 times that 5 to the x. But I'm not thinking 0.5. And neither are the rest of you. When we look at that, we should be thinking, well, that's -1/2. So I have to take each one of these times -1/2. Get my new blue graph. All right, top times top, bottom times bottom of fractions, so -1/50. Ooh, that's going to be really close to the x-axis. -1/10, still pretty close to the x-axis. -5/2, -2.5, it's finally starting to pull away. And then -25/2. So negative 12.5, which means it gives us something in there. All right, so now with my blue, I'm at negative 2 and just a teensy little bit below x-axis. Same thing at negative 1, just a little bit more. At 0, oops, I lost that one. It got squashed. I'm at negative 1/2. At 1, I'm at negative 2.5. And at 2, I'm at negative 12.5. So I'll kind of aim about there. So it's a good place to aim. And connect those up in a smooth curve. Aiming towards my E here. So it did reflect over the x-axis, we can see that. And again, the compression is just really hard to see, but we know that one there was supposed to take us all the way up to 25, and this one is only taking us to negative 12.5. So the numbers tell us it's been squished. So they want to know, does a stretch, compression, or reflection affect the asymptote? Well, we've only seen 2 of them. But didn't it stay at the x-axis for both of them? So the answer is no. No, didn't affect the asymptote at all. So having vertical stretch, having a reflection, does not affect the asymptote. It affected our range, but it didn't affect the asymptote. So here's what they're getting at with everything we looked at, including the getting ready, and that is a horizontal shift, this little H, when you're using exponential growth and decay, could be a vertical stretch or compression. We're not really going to use it that way. I mean, we're going to keep doing what's been working for us. We're going to graph our parent, and then we're just going to use H and K to slide it where we need to go. But the thing about these is, and I'm sure you noticed this, when we did the square root, it was like, oh, this is always our parent. It's always going to look this way. Anymore, because now if we have a different base, that changes the numbers that we're going to see. So these are kind of individualized. There's going to be a lot of things that are the same, but if the base is different, well, we're going to have to do a little bit more. So this one says, how did the graph of each function compare to the graph of the parent function? And for this one, our parent function would just be y equals 2 to the x. So what they're really asking here is, what's the x minus 4 doing to the graph? What is it doing? For the right, exactly. Remember with the x, it's always backwards. So translate 4 units right. I like that. Because what that means is, all I'm going to have to graph in my table, y equals 2 to the x. There is no number out in front, so a is 1. That's not going to affect my shape graph. So, if x is what we're looking for, then it's 2 to the x. I start thinking about numbers here. Well, if it's a 2, is it growth or decay? Growth. So I probably don't need a whole lot of negatives, but I'd like a few more of the positives. So maybe -1, 0, 1, 2, 3. So that I'm sure I'm seeing how fast this graph is going up. And then I just take 2 and I raise that power. 2 to the -1, what do you get? 1/2. You flip it. 2 to the 0, 1. 2 to the first, 2 squared. 2 to the third. We've seen those numbers before. That's not too bad. So -1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. Now we're not going to make that solid. And that's because this is our shape. That's the shape our graph is going to have. But we said it had to move. Where's it moving? 4 to the right. Okay, so let's do some counting. 1, 2, 3, 4. 1, 2, 3, 4. that one will make solid. Because that's our answer. That's the one that has 2 and the x minus 4, because we had to move it 4 units to the right. Looks exactly like we said it was going to look. Taking the whole thing and moving it 4 units to the right. What's our asymptote? It's still y equals 0. Still y equals 0. So far, we haven't changed our asymptote at all through any of these. And now we get to this one. And here's what I want you to do. What I want you to do is you're going to get a partner. You're going to talk about this 1/2. You're going to tell each other whether or not this is decay or growth. Now, if it's decay, you're going to want a couple extra negatives and not so many positives. If it's growth, you're going to want just a few of the negatives, but more of the positives in your table. And we're going to skip a step that we've been doing, and we're going to go directly to that. We're going to graph the whole thing. I don't like that 0.5 there, but I'm going to give you calculators because some of you will probably use them because you won't want to do 1/2 in a calculator. So you'll put your numbers here. You'll come up with the shape graph. You'll put it on there without having it be solid. I don't care if you do dashed, dotted, whatever you have to do. And you and your partner are going to talk through which way you need to move it and how you're going to go about it. Now, why am I doing all of this and talking about this beforehand? Because look at how you have to move it. You might not be able to go by 1s. You might need to make your graph go by 5s or 10s or something like that, so you'll be able to see things a little bit easier. But I'm going to get you candy partner while you start thinking about that. First step is growth or decay. That'll determine what numbers you want in your table. Maybe you could write down which way you think it's going to move so you can talk to your partner about that when you get with them. We are missing 2. Can you hang on until you have your partner? Because they would appreciate knowing who they're with. Who got the Tootsie Roll? We have somebody that's gone today. But I know I have 3 dum-dum suckers out there. This is counted here. So dum-dum suckers, where are my dum-dum suckers at? Devin, you get 2, but don't go with the dum-dum people. Go with the Tootsie Roll. All right, candy up in the air. Make eye contact. Get together. And if you need a calculator, stop by and see me on the way to get with your partner.
What numbers would we use on the X?
Calculators?
Do you remember the question?
That's because now we have to check the base. So the basis for decay, how we want to use
Basically. Yeah.
Is it?
I think it will be checked once.
Oh. Yeah.
I don't know. I can't see anymore.
You are just going to take
That I can't see it exactly.
so what you can do is maybe that faster.
Because I literally put my parentheses. You know, I know what it is. So, like, there's the answer to that
especially the graph.
Let's talk through your first step with your partner. Was this one decay or growth?
Okay.
Decay, got 1/2. So a few more negatives would be good. Not so many positives. So maybe like -3, -2, -1, 0, 1, something along those lines. Also, don't forget if you're using the calculator, you can do that cheat where you do 20 times 5 to the, and then you can do second enter and just change the -1.
It's 0.5.
Oh, thank you. Well, either way.
Yeah.
Make it a little easier to punch in. Huge, because first of all, we've got that. Everybody getting those uncomfortably big numbers, right? Yeah. That's when you have to decide what to go by instead of by ones. What did everybody decide on the lines? Did you go by 10? 20? Okay, so you have to. You're not going to be able to put this graph on there any other way. Yeah, we can still go by ones on the x-axis. It's just on the y-axis. You're going to have some trouble. The number is just big and big, you know. It makes it really hard to see what a big transformation is by moving it 10 units up. So it's a poor choice on their part to throw that 20 up in front of it. Which way do you move it 10? Up, up. Remember, it's not with the x, it's not attached to the x power. 10 up. do a little fixing because you accidentally went 10 for right. K is always by itself. K is a loner. K is that student in class that pulls the hood over their head and doesn't talk to anybody. K is a loner.
Jeez.
Talk to your partner. Asymptote.
Yeah, that's all. So it never comes over
We get a new asymptote with this one?
Nope.
Yes, we did. If our asymptote was at y equals 0, and we just moved everything up 10 units, where's our new asymptote? Y equals 10. So K is finally the piece that's going to move the asymptote for us. So that actually helps us out if we're formula people. Because if we're formula people, we can write down that the asymptote will always be y equals k. Every time. Because we're shifting this whole graph up. Originally, it would have had an asymptote of 0. But everything moves up, including the asymptote. So the new asymptote will be y equals 10. It's got to happen. So now what you're going to do is you're going to make your fabulous little chart here with your partner.
One question. So every time there's like a number in the please.
It is. It is. Every time, because we're shifting that asymptote from 0 to that, whatever it is.
That's not going to be like the last.
It's exactly for growth and decay, things get a little weird. They do. They do. All right, so they want us to compare the domain range and asymptote from our original y equals 20 times 1/2 to the x to y equals 20 times 1/2 to the x plus 10. What's the domain for both of these? Yeah, all those. We don't have any x's we can't put into these things. Bless you. But the range changes because this one didn't have an up and down shift. Our range was just going to be y is greater than 0. But when you shift the whole graph, you also shift the asymptote. So now this one is going to be y is greater than 10. So before the shift, what was all of our asymptotes up to this point? 0. Not anymore with this one. What was it? 10. Y-intercept? Well, with this one, it was 0, 20. That fit everything we knew. It was supposed to go through 0, 8. But wait a minute. We had to move that up 10 units to get this one. So if we move it up 10 units, which one of these is getting bigger, the 0 or the 20? The 20. That's y, up and down. So this would be 0, 30. So things change when we have that k. Now, they're asking us a horizontal shift. Those are the ones we did before. We moved one right and left. Did that change our asymptote? No. How about the up and down shift we just did? Absolutely. Yes. In fact, this is where we find out y equals k will always be our asymptote. Always. Now, for these two, with you and your partner, all I want you to do is go through and say, hey, here's the transformations that I see. So the 4 is the base. That's not part of what we're looking at. We're looking at what is this 2 doing here, writing it down. Then we're going over here and we're saying, okay, what is this 5 in front doing and what is this 5 in back doing? So talk to your partner and write down what those transformations are going to be.
It's left to me. Not right. Ah. Out.
That was good to see. I'm wandering around. So far I didn't see anybody that accidentally said to the right. You know, we're remembering to catch that. What did the 5 in front? Vertical stretch, factor of 5. This 5 we're talking about right now. Vertical stretch, factor of 5. How about that 5? 5 up. Translate up 5. Here's what I want you to tell your partner. I want you to tell your partner which one of these would have a new lesson. That went really fast. You're saying B. How come? It's got a vertical translation. Vertical translation is going to change that. A horizontal is not. So there we go. I feel like we didn't get lots done today, but that's because all of these are a little bit different. There we go.
What?
It's not very long because I knew we weren't going to get real far today. Each one of these is a little bit different because you first have to say, hey, is this growth or is this decay? Now, how am I going to get that parent function graph on there? Now I've got to do my counting. Up, down, right, left. So 10 through 17 are going to be the ones you're going to do. 10 through 15 are graphing. So you probably want some graph paper noodles. I think that's it for the graphing. Let me double check real quick. But that'll make it go a lot faster if you just add a piece of graphing.
7
Yep.
to 15?
It'll be 10 through 15 that you do the graphing for. The 7 is an explain. 8 is an explain. 9 is an explain. Yeah, so 10 through 15 will be the graphing.
What am I explaining?
Well, in the first one, you're going to explain how to tell whether something's exponential or it's up where it says, do you understand? Oh, your numbers don't match my numbers in my book.
Birds came from whole.
Oh, I must have an older edition for the teacher's edition up there.
Put that over.
That's the wrong one.
Yeah, well, I had the good gravy today. I gotta get some sleep. 7 to 15, all graphing. 18 is a graphing. Okay, so yeah, you'll need to definitely need graph paper.
18.
Yep. We can't do 22 yet. I'm gonna have to take that one off. I know that'll make you sad,
Yeah.
but we can't do that one yet.
Something, everything else is good.
Yes, The rest of it is good. So all the graphs are gonna come right here in this beginning part. Yeah, 2 Algebra 2 classes, both in different parts of the book right now, so. I ran off a whole lot of graph paper yesterday, so all kinds of graph paper up there for you.